China just certified a combustion engine with 48.41% thermal efficiency. You heard that right, 48.41. To put that in perspective, the average Toyota or Volkswagen you see on the road today converts just 30% of its fuel into motion. The other 70% disappears as heat. Gone. Wasted. Every single time you fill up. And the craziest part isn't the number itself, it's how they got there, what they built to do it, and what it means for every car company on the planet that thought this ceiling had already been reached. To understand why engineers around the world went quiet when this was announced, you need to start with a number that ruled the industry for over a century. The number that broke the internet. Picture a bucket with a hole in it. You pour in 10 liters of water, and 7 of them pour straight out onto the floor before a single drop does any useful work. That is your car engine. That has always been your car engine. And for over 100 years, the entire automotive industry looked at that leaking bucket and said, yeah, that's about as good as it gets. Here is what most people never think about. When you burn fuel inside a combustion engine, only a fraction of that energy actually pushes the piston down and turns the wheels. The rest becomes heat. It radiates into the engine block, it escapes through the exhaust, it bleeds into the air around you. A typical engine from Toyota, Volkswagen, or Ford converts roughly 30% of the fuel's energy into motion. 30%. That means every time you spend $50 at the pump, 35 of those dollars are essentially lighting themselves on fire and disappearing into the atmosphere. Engineers have a word for this. They call it thermal efficiency. And for decades, the global benchmark, the number every serious automaker quietly chased, sat somewhere between 30 and 35% for a standard production engine. That was the world. That was the ceiling most people accepted, without question. Then Toyota changed the conversation. Over the course of roughly 2 decades, and with billions of dollars in research and development, Toyota's engineers pushed their hybrid engine thermal efficiency to 41%. 41. That was not a small jump. That was a generational leap. The engineering community treated it like a moon landing. Toyota won awards. The number was cited in academic papers. Industry analysts declared it the practical limit of what physics would allow in a real-world production engine, not a laboratory experiment, not a prototype, but something you could actually buy and drive. Now here is the detail that puts everything into perspective. That finish line, the one Toyota spent 20 years and billions of dollars reaching, lasted less than a decade before a Chinese automaker walked past it, not crept past it, not edged past it by a fraction of a point in a controlled lab environment, walked past it. Geely, a company that had virtually no serious global automotive presence 15 years ago, just had its engine certified by Guinness World Records at 48.41% thermal efficiency. That is 7.5 percentage points above Toyota's celebrated ceiling. In engineering terms, that is not an incremental improvement. That is a different conversation entirely. And the certification matters. This was not a press release. This was not a marketing claim buried in a brochure. The Guinness World Records certification means independent verification. It means the number is real, the conditions were controlled, and the result stands. Most people hear 48.41% and nod along without truly feeling it. So before you move forward, sit with this for a moment. The engine was invented in Europe. It was refined to what the world believed was near perfection in Japan. And the efficiency record now belongs to a company from China that barely existed on the global stage when the iPhone was first released. But understanding the record is only the beginning. To understand how they broke it, you need to go back to the wall that everyone said couldn't be moved. A century of good enough. Here is something the auto industry never advertised. The combustion engine has always been extraordinarily wasteful, not slightly wasteful. Not inefficiently wasteful in a way that was being actively fixed. Brutally, structurally, fundamentally wasteful, and the people with the most power to change it had very little financial reason to do so. Think of it like a restaurant that burns 60% of every meal it cooks before the plate ever reaches the table. The restaurant stays open, customers keep coming, the owners keep profiting. Nobody with a seat at that table is rushing to redesign the kitchen. When the internal combustion engine was first commercialized in the late 1800s, thermal efficiency sat somewhere around 10%. 10. 9 out of every 10 units of energy in the fuel went nowhere useful. But the engine was still revolutionary because nothing else could do what it did: move people and goods at scale, on demand, without rails. The inefficiency was tolerable because the alternative was a horse. Over the following decades, engineers chipped away. 12% became 15, 15 became 20. Each jump required serious innovation, better metallurgy, higher compression ratios, improved fuel quality, more precise ignition timing. And each jump came slower than the last because the easy gains were taken first. By the mid-20th century, standard production engines were hovering around 25 to 28% efficiency, and the pace of improvement had slowed to a crawl. Here is what most people get wrong about this period. The slowdown wasn't purely technical, it was economic. A more efficient engine means less fuel consumed. Less fuel consumed means less revenue for oil companies, less urgency for consumers to upgrade vehicles, and less differentiation for automakers who had built entire supply chains around existing architecture. The incentive structure of the 20th century automotive industry was not designed to reward radical efficiency gains. It was designed to reward incremental ones just enough to market, never enough to disrupt. Then two things changed simultaneously. Oil prices became volatile enough to make efficiency a selling point, and emissions regulations in Europe, Japan, and eventually the United States began forcing automakers to care about combustion quality in ways the market alone never would have demanded. Toyota responded to both pressures with the Prius program, and eventually with the hybrid engine development that pushed their thermal efficiency toward 41%. That achievement genuinely deserves respect. It required solving problems that had stumped the industry for generations: managing heat rejection, controlling combustion timing at extreme precision, and integrating electric assistance without sacrificing the efficiency gains from the combustion side itself. But here is the brutal catch that nobody in the Western press wanted to say out loud. Toyota's 41% was achieved under the assumption that certain thermodynamic trade-offs were permanent. That you could not simultaneously maximize compression, minimize heat loss, and optimize combustion shape without one of those variables collapsing the others. That the physics of the situation drew a line, and the line was approximately 41 to 42% for anything that needed to survive daily use in the real world. Geely's engineers read that assumption, and then they decided to attack all three variables at the same time. The physics wall everyone said couldn't be broken. Imagine you are trying to boil water in a paper cup over an open flame. The flame is real, the heat is real, but the cup is losing heat faster than it can build up, so the water never quite reaches boiling point. You can make the flame bigger, but the cup burns through. You can make the cup thicker, but then the heat transfers even slower. Every solution creates a new constraint. That is, combustion engine engineering in one image. The reason thermal efficiency has a ceiling is not laziness, it is physics. Specifically, it is thermodynamics, the branch of science that governs how energy moves, converts, and inevitably loses itself to heat. There is a theoretical maximum called the Carnot efficiency limit, which describes the absolute best any heat engine could ever do given the temperature difference between its hot and cold zones. For a real-world combustion engine operating at realistic temperatures, that theoretical ceiling sits somewhere around 60%. But between the theoretical ceiling and the practical one sits a canyon filled with problems that have resisted a century of engineering effort. Here is what that canyon actually looks like in practice. The first problem is knock. When you compress a fuel-air mixture, it heats up. Compress it enough, and it ignites before the spark plug fires uncontrolled, chaotic combustion that sounds like a knock and can destroy an engine from the inside. To push efficiency higher, you want higher compression. But higher compression triggers knock. Engineers have spent decades managing this trade-off with premium fuel grades, precise ignition timing, and cooled exhaust gas recirculation. Every solution has a ceiling of its own. The second problem is heat loss to the cylinder walls. When the fuel ignites, it needs to push the piston down with maximum force. But the combustion chamber walls are cold relative to the burning gases, so heat bleeds from the flame into the metal before it can do useful work. The faster the combustion happens, and the more completely the flame fills the chamber, the less heat escapes. But getting the flame to move faster and fill the chamber more completely without triggering knock or uneven burning is, in conventional engineering, extraordinarily difficult. The third problem is friction. Every moving part in an engine that touches another moving part steals energy. Pistons against cylinder walls, bearings against shafts. The hotter the engine runs overall, the more the metal expands, and managing thermal expansion across an engine that needs to survive hundreds of thousands of kilometers requires tolerances so precise they are measured in micrometers. A micrometer is 1/1000th of a millimeter. The margin for error is essentially invisible to the naked eye. Now here is the part that blows people's minds. These three problems, knock, heat loss, and friction, do not sit in separate boxes that engineers can solve one at a time. They interact. The solution to knock affects heat loss. The solution to heat loss affects friction. Pull one thread and two others move, which is exactly why the industry converged on 41% and stopped. Not because they gave up, because the variables were genuinely interconnected in ways that made further progress feel like pushing water uphill. Geely did not find a way around those problems. They found a way to attack all three simultaneously in the same engine, using three distinct systems that each solved one problem without making the others worse. And that combination is what broke the wall. How they actually did it. Most breakthroughs in engineering history come down to one insight that unlocks everything else. One material, one geometry, one timing adjustment that cascades into a revolution. Geely's 48.41% did not work that way. There was no single magic moment. What they built was a stack three separate innovations, each solving a different part of the problem, each designed so precisely that together they produced a result the industry had declared impossible. The first innovation is called the Euler Tornado combustion system. And before you picture something complicated, picture a bathtub drain. When water spirals down a drain, it doesn't flow in a straight line. It rotates, it accelerates, and every molecule of water is moving with the current rather than sitting still waiting to be pushed. Geely's engineers applied that same principle to the air entering the combustion chamber. The Euler Tornado system forces incoming air into a high-speed spinning vortex before it ever mixes with fuel. By the time ignition happens, the fuel and air are not loosely combined. They are intimately, uniformly blended at the molecular level, rotating together at speed. What that does to combustion is dramatic. Instead of a flame crawling from the spark plug outward across the chamber, losing heat to the walls with every millisecond it travels, the flame front explodes outward simultaneously in all directions. The combustion is faster, it is more complete, and because it finishes before the heat has time to bleed into the cylinder walls, dramatically less energy is lost. The heat that used to escape becomes motion instead. That solves the heat loss problem. Here is the detail that engineers don't want to admit about conventional combustion chambers. The shape and flow of air inside them has been optimized incrementally for decades, but the fundamental approach air enters, fuel is injected, spark fires, flame travels, was never fundamentally rethought. The Euler Tornado system rethinks it at the entry point. Before the spark, before the fuel, the efficiency gain begins. The moment air enters the engine. The second innovation is the split thermal management system, and this one required solving a contradiction that conventional engineering treated as permanent. To prevent knock at high compression, you want the cylinder head, the top of the combustion chamber, to run cold. Cold surfaces resist the pre-ignition that destroys efficiency and engines. But to reduce piston friction, you want the engine block where the pistons move to run warm. Warm metal expands to tighter tolerances, reduces the gap between piston and cylinder wall, and cuts friction losses significantly. Cold head, warm block. In a conventional engine, those two requirements fight each other because the cooling system treats the engine as a single thermal zone. Geely's split thermal management system divides the engine into two independently controlled temperature zones, running the cylinder head and the engine block at different temperatures simultaneously. Two conflicting engineering goals, solved at the same time, in different parts of the same engine. The third innovation is the 11-in-1 EDHT drive unit. Forget the gearbox, you know. Forget the separate components, the transmission, the generator, the inverter, the electric motors, each housed individually and connected by shafts and cables that each introduce their own friction and energy loss. The EDHT unit packages the combustion engine, a generator, 2 electric motors, and all associated power electronics into a single unified housing. 11 components, 1 unit. Managed by an artificial intelligence system that recalculates the optimal power routing between combustion and electric 50 times every second. 50 times per second, that is faster than a hummingbird beats its wings, running continuously, invisibly, every moment the vehicle is in motion. Together, these 3 systems do not just add efficiency, they multiply it. The number that makes Western engineers uncomfortable. Everything you have heard so far, the Guinness record, the 3 innovations, the physics wall is the story of how. Now here is the story of what it actually produces when you put it in a car and drive it. Geely installed this engine and its 11-in-1 drive unit into a full-size SUV, not a compact city car engineered specifically to game fuel economy tests. Not a lightweight prototype stripped of everything that makes a vehicle usable. A full-size SUV, the kind of vehicle that seats 5 adults comfortably, carries luggage, and weighs over 2 tons on the road. Picture a vehicle the size and weight of a Toyota Land Cruiser, something that wide, that tall, that heavy. Now imagine it returning 2.22 liters of fuel per 100 kilometers under certified test conditions. 2.22. You heard that right. For comparison, a Toyota Corolla, one of the most fuel-efficient conventional sedans on the market, averages somewhere between 5 and 6 liters per 100 kilometers in real-world driving. Geely's full-size SUV is using less than half that, in a vehicle that weighs significantly more. Here is what makes this incredibly exciting for anyone who has ever done a long road trip. That fuel consumption figure translates to a total range of over 2,000 kilometers on a full tank. 2,000 kilometers is roughly the driving distance from London to Warsaw, from New York to Miami and back, from Karachi to Kabul and back with fuel to spare, in one tank, in an SUV. Now, here is the part that nobody in the Western automotive press lingered on long enough. That range figure does not just compete with combustion vehicles, it competes with electric vehicles. The longest range production electric vehicles available today, vehicles from Lucid, Mercedes, and Tesla's top configurations offer somewhere between 600 and just over 800 kilometers of range under ideal conditions. Geely's hybrid SUV, running on a tank of fuel available at any petrol station on the planet, offers more than double that, without a charging network, without a 30-minute fast charge stop, without range anxiety on a motorway in January. The certified fuel consumption of 2.22 liters per 100 kilometers also means something specific in terms of carbon output that the industry rarely calculates publicly. At that consumption rate, the vehicle emits roughly 52 grams of carbon dioxide per kilometer. The European Union's current regulatory target for new passenger cars, the standard that automakers spend billions trying to meet, is 93 grams per kilometer. Geely's SUV is producing 43% less than the legal requirement in the world's strictest automotive emissions market, in a full-size SUV. Here is the brutal catch that the competitive analysis always skips. This is not a concept car. This is not a 5-year roadmap. This is a certified production-ready powertrain in a vehicle that exists today. And the automakers watching this in Stuttgart, in Detroit, in Nagoya, are doing the same maths you are doing right now. Because if a full-size SUV can achieve these numbers in production trim, the assumptions that shaped 50 years of automotive strategy just became negotiable. Why every automaker is quietly recalculating. Here is something worth understanding about how the global car industry actually works. Automakers do not just compete on the vehicles they sell today. They compete on the technology bets they made 5, 10, 15 years ago. The factories they built, the supply chains they locked in, the regulatory strategies they lobbied for. A breakthrough like Geely's 48.41% does not just threaten one model line, it threatens the entire strategic architecture that major automakers have been constructing for the last decade. Think of it like a chess game. where one player suddenly reveals they have been playing a different game entirely and their pieces are already in position. For the last 10 years, the dominant narrative in the Western and Japanese automotive industry has been a single, confident prediction. Combustion is dying. Electrification is the only viable path forward. And the race worth running is the battery race. Volkswagen committed hundreds of billions to EV transition. Ford restructured its entire company around an EV division. General Motors announced the end of combustion vehicles by 2035. Toyota, more cautious than most, hedged with hybrids, but even Toyota's long-term roadmap pointed toward a world where the combustion engine's role would steadily shrink. Those bets were not irrational. They were made based on the assumption that combustion efficiency had reached its practical ceiling, that the only meaningful efficiency gains left were on the electric side, that improving a combustion engine beyond 41% for real-world production use was not a viable path worth serious investment. Geely just invalidated that assumption. Now here is the part that most people get wrong when they hear this story. The threat is not simply that Geely built a better engine. The threat is what a better engine does to the economics of electrification. Every argument for rapid EV adoption rests on a comparison to combustion vehicles that are assumed to be inefficient, expensive to fuel, and environmentally costly. An SUV doing 2.22 liters per 100 kilometers with 2,000 kilometers of range rewrites that comparison entirely. A consumer in 2026 does not choose between a concept and a principle. They choose between vehicles. And if a combustion hybrid offers longer range, lower purchase price, zero dependence on charging infrastructure, and dramatically lower fuel costs than a comparable EV, without requiring any behavioral change around how you refuel, the purchasing decision becomes genuinely complicated in ways that Western automakers' current product roadmaps did not prepare for. Here is what makes this moment particularly significant for the competitive landscape. Geely is not a niche manufacturer. Through its subsidiary and ownership structure, Geely controls Volvo Cars, owns a significant stake in Mercedes-Benz, and manufactures vehicles across multiple brands and price points that reach markets from Europe to Southeast Asia to South America. The 48.41% engine is not going into one car for one market. It is a platform technology that can propagate across an entire global portfolio. The internal combustion engine was invented in Europe. It was refined to what everyone believed was its peak in Japan. And the company that just broke the world efficiency record is the same company that bought Volvo for $1.8 billion in 2010, when most of the Western automotive industry smiled and assumed it would. Struggled to manage a premium European brand. Nobody is smiling now. And the real question, the one that reshapes everything, is what this means for the road ahead. The world you are about to drive in. Here is what this actually means. The combustion engine was declared finished, not struggling finished. The Western automotive industry placed a collective trillion-dollar bet on that declaration. Factories retooled, supply chains restructured, entire government policies were rewritten around it. Geely just proved the declaration was premature. 48.41% thermal efficiency, 2.22 liters per 100 kilometers, over 2,000 kilometers of range, in a full-size SUV. Certified, production ready, available now. You are not watching the end of the combustion engine. You are watching it get reinvented by people nobody saw coming in the same decade everyone agreed it was obsolete. The engine was born in Europe. It was perfected in Japan. And the efficiency record that will define the next era of transportation belongs to a company that barely existed on the world stage when you bought your last car.